Video 4-5, Exceptions to Electron Configuration Rules, Quantum Numbers, Emission Spectroscopy. Okay, so by now you should be good at writing out electron configurations just using the periodic table. Okay, but there are some exceptions you need to worry about. Okay, so write down the noble gas electron configurations for these two elements, copper and chromium. Okay, pause the video, write it down. Okay, so for copper, it should be 4s2 3d9, and for chromium, same row. So you're starting with argon, 4s2 3d4. Okay, but it turns out that the actual configuration for copper is, and chromium is not what we expect it to be. Okay, for copper, it's 4s1 3d10. Now, total number of electrons is still the same. You still got 2 plus 9, that's 11. 1 plus 10 is still 11. So all electrons are still accounted for. And for chromium, it's 4s1 3d5, not 4s2 3d4. Okay, so the question is, why is it like that? Okay, well, let's go look at the Aufbau diagram. Okay, we would expect that if you put the electrons in, it should end up like this. Okay, the last electron should end up going into the 3d orbital. Okay, now, the actual configuration is that it looks like this. Okay, notice this one right here is empty and it ended up going up there. Okay, and for chromium, something similar. We have this one completely empty. Okay, and the actual configuration, that electron moved up there. Okay, now, why is that? Why did it do that? Okay, well, remember, the reason why anything does anything is atoms are trying to be lazy. They're trying to become more stable. Okay, if the d orbitals are either half filled or completely filled, this tends to stabilize the configuration. Okay, and only one electron can jump up from that lower s orbital, and that's the only place they can jump from, is that s orbital up to a d orbital. Okay, why? Well, let's go back and look. What happens if both of these were to jump up? Okay, now why are they jumping? They would rather be separated, have one there and this one not there, because this basically creates repulsion. Okay, so this is known as a pseudo noble gas configuration when it's either a D5 or a D10. Okay, and you cannot jump 2 electrons because you cannot have a 4s or any s orbital be completely empty and have electrons in the energy level above it. Okay, this cannot be completely empty. Okay, so we can expect other atoms to be doing that. Anything that ends in an S2D4 and S2D9, okay, the same basic reason that we talked about before. One of these will jump up and become an S1D5, and one of these will jump up to there and become an S1D10. Okay, so which elements do we expect to do that? Well, it should be the ones right below, chromium and copper. Okay, all of them do run this exception, except for tungsten. Tungsten doesn't run it, so tungsten is an exception to the exception. Okay, tungsten keeps its S2D4 configuration. Okay, so the ones that you are responsible for knowing are the D4s and the D9 configurations. They don't turn into that. The only one that does do a D4 is tungsten. Okay. And there's a lot of other exceptions in transition metals, especially in period 5 of the transition metals. If you look on the periodic table that has these in your textbook, for example, okay, you'll see a lot of them, but the only ones you are responsible for knowing are the D4s and the D9s. Okay, now next thing we look at, quantum numbers. Okay, every electron in an atom has a unique set of 4 quantum numbers. Okay, now the first number that you give it is called the N number, or the principal quantum number. This is simple. Figure out where the electron is located, what energy level, what orbital, etc. Okay? And the first number basically is going to be same as the energy level of that electron. Okay? The second number, we give it the symbol L. This is called the angular momentum quantum number. This basically tells you which type of orbital that electron is in. Okay? Whether it's an S, P, D, or F orbital. And the values can run from 0 to n minus 1. Okay, so the possible values, if it's in row 4, okay, so if n is equal to 4, the values can run from 0, 1, 2, or 3. n minus 1 is going to be equal to 3. Okay, and 0 corresponds to an s orbital. 1 corresponds to p orbital, d corresponds to a d orbital, 3 corresponds to an f orbital. Okay, so if the electron were in a 4s orbital, okay, our first number would be the energy level, 4. Our second number would be the type of orbital, so we'd be picking 0. Okay. The third number, m sub l, these are the magnetic quantum numbers. Okay. And this identifies a specific p, d, or f orbital. Remember, these are degenerate orbitals. Anytime you have p orbitals, there's 3 of them. There's 5 d orbitals. There's 7 f orbitals. Okay. The values run from negative L to positive L. So, if we said L was equal to 1, that meant it was in a p orbital. Possible values for the p orbital, the m sub L values would be negative 1, 0, and positive 1. Okay, now notice there's 1, 2, 3 values, and because there are 3 p orbitals. Okay, and the last one is for our spin. Okay, m sub s, a spin quantum number. And remember, our spins basically just mean the electron's either pointing upward or downward. Okay, so just use to differentiate between 2 electrons in the same orbital. Okay, remember, you cannot have 2 electrons with the same spin in the same orbital. And the values are either plus 1/2 or minus 1/2. Okay, now the plus does not have to mean that it's up, and the minus 1/2 does not have to mean that it's down. This can be for up or down spin. But if you say it's plus 1/2 is going to be down, then that means that negative 1/2 has to be the up. Okay, so determine a set of quantum numbers for each of the following electrons. Okay, so let's take a look at this first one right here. Okay, the first number is the energy level, so it has to be 1. Okay, the second number is the type of orbital. It's an s orbital, so s is equal to 0. Okay, the third number, the possible values are negative L to positive L. So negative 0 to positive 0, meaning there's only one possible value, 0. And since it's an upspin, let's call it plus 1/2. Okay. Now the only thing we have to do is, once we said plus 1/2 is up, we have to be consistent all the way through with the rest of the electrons. Okay. The next electron, it's also in the energy 1, so that's 1. It's also in an s orbital, 0. Okay. And again, if it's an s, there's only one orbital, so its value must be 0. And since 1/2 was for the up, that's a downspin, we have to call it negative 1/2. Okay. Next one there. Energy level 2. It's also an s orbital, so it's 0. Only one possible value, 0. And upspin, so plus 1/2. That one there, 2, 0, 0, negative 1/2. Okay. Notice, if the electrons are in the same orbital, the first 3 numbers have to be exactly the same. Okay, now the 2p. Energy level 2, it's a p orbital. So the L value for p was 1. Okay, now the m sub L values, there's more than one possible value. The values can run from negative 1, 0, or positive 1. Okay, so we pick one of them. Doesn't matter which one of these is called negative 1, which orbital is called 0, which one's called positive 1. Okay, just one. Once you assign one of these orbitals a value, the other 2 cannot have that same value. Okay, so we'll call it -1. It's an upspin, so +2 or +1/2. Okay, next orbital, it's also in a 2p, so it has to be a 2 and a 1. Okay, it's a different orbital, so you can't use -1. So our values are either 0 or +1. Okay, so we'll pick 0, upspin, so +1/2. The next one, 2, 1, energy level 2, p. It's in a different orbital from the -1 and the 0. So the only remaining value is +1. Okay, and upspin +1. Okay, and the last one there, it's in the same orbital as this electron. So like we said before, the first three numbers have to be the same. 2, 1, -1, and the only thing different is the spin, -1/2. Okay, every electron has a different set of quantum numbers, but not necessarily a definite set of quantum numbers. Okay, meaning, this electron right here has to be 200. It didn't have to be +1/2. It could have been -1/2. Okay, and this electron on right here would have had to been, if we called this -1/2, that would have had to been +1/2. Okay, the electron right here, let's say this first one. Okay, the only numbers that had to be there, 2 and 1. Didn't have to be -1. It could have been 0 or +1. Okay, so if I told you find the electron that has the quantum numbers 3, 1, 1, 1/2, you could not necessarily tell me which one of them. All you can tell me is that it's one of 6 electrons that could be in a 3p orbital. Okay, but if there's six electrons in that orbital, any one of those 6 could have that set of quantum numbers. Okay, last thing we'll look at, emission spectroscopy. This is for your one of your labs. Okay, when electrons are in the ground state and they gain energy, they jump up to an excited state. Okay, this you guys already know. Okay, and when the electrons fall back down to a lower energy level, they're not going to stay in the excited state. They have to give off light. Okay, they're giving off energy in terms of a photon. Okay, and we know that they can only jump to certain energy levels. They can't jump to anywhere. It's like walking up the ladder, not walking up a ramp. Okay, so the energy levels are quantized. Okay, and if we analyze the light, okay, we can figure out which energy transitions were taking place. Okay, so, for example, compare the emission spectrums of hydrogen and helium gases. Okay, hydrogen gas has kind of this pinkish color to it. Helium has more of a bluish, okay, almost white color to it. Okay, and if you were to take this color, run it through a prism, okay, you would see colors that look like this. Okay, and if we take the helium and run it through the same prism, you don't get a continuous spectrum, you get a bright line spectrum, and it's going to look like this. Okay, you notice you may get similar colors, but the wavelengths are different that they're appearing at. Yes, you have a yellow here, but you have yellows here at different wavelengths. Okay, now, what's taking place? Well, hydrogen, okay, this is our 1s, helium, this is our 1s. Hydrogen has to be a molecule, so it has to have 2 electrons in it. Okay, so what's possible? Well, it could jump up here and fall back down. It could jump up here and fall back down. It could jump up here and fall back down. 2 electrons are both the same spot, so all the same transitions possible. Okay, helium could jump up to here and fall back down. It could jump up to here and fall back down. It could jump up to here and fall back down. Okay, so let's call this 2. Let's call this energy level 1. Let's call this 3, 4. Okay, same transition, right? It goes from 2 to 1. Here it's going from 2 to 1. Here it goes from 3 to 1. Here it goes from 3 to 1. Okay, so in helium and hydrogen, the electrons can jump up the same energy levels, fall back down again. Now, if the energy level transitions are exactly the same, how come the colors aren't the same? Okay, well, must be a simple reason. Even though you're going from 2 to 1 on this one, and you're going from 2 to 1 on this one, the change in energy, and the change in energy is going to give you the frequency. And the frequencies are different because you get different colors, different wavelengths. Okay, so if, let's call this nu 1 and nu 2, if frequency, number 2, if frequency 1 is not the same as frequency 2, that must mean the change in energy from 1 is not the same as the change in energy from 2. Okay, so in other words, the gaps are different. Delta E here and delta E here are not the same. Okay, and that is different for every element. That's why every element gives you its own distinct color, its own distinct spectrum. So, for our review, going back to quantum numbers, how will the quantum numbers of two electrons that are in the same orbital, how will they differ?